Hey guys, today we're going to look at friction a little bit more in depth. I know we've used them in FNet problems, but I still want to give you more information about it. So there are two types of friction that affect motion. The first type is static friction. It is the force exerted between surfaces when two objects are not in motion. This force becomes a larger value as you push against an object, but once you overcome static friction, the object begins to move and you have to apply a lower amount of force. So the example that I always use for this is if you were trying to move a full dresser across your bedroom. You have to apply a large amount of force to get it moving, but once it starts sliding, the force that you have to apply lessens a little bit. That's how you know you're dealing with static friction. You push and you push and you push, and eventually once it starts to move, you don't have to push quite as hard anymore. So for static friction, I'm going to make a graph that's going to give you a little idea of what this means. The bottom is time in seconds, and the y-axis is force in newtons. As you apply your force, it increases and increases and increases, and once you hit that threshold of friction, the force you have to apply decreases quite a bit. So this force is always changing. The numerical value is always changing. The second type of friction is kinetic friction. This is the force exerted between surfaces when one or both of the objects are moving. So once you overcome static friction, you move into having kinetic friction. This is a set value and does not change if you apply more force. Once it is moving, it has the same value of kinetic friction at all times. So why does friction occur? At a microscopic level, all surfaces are rough. When surfaces touch, the highest points are in contact and temporarily have a bond. To make the object move, you must break those bonds. So I'm going to draw a little drawing down here. Here's the surface of two objects. And when they come close to each other and in contact with each other, these two high points create a bond. And you have to break this bond for one object to move to the right and the other object to move to the left. And then the next two surfaces bond, and you have to break that bond, and then the next two surfaces bond, and you have to break that bond, etc., etc. So friction is the creation and the having to break constant bonds between the high and the low surfaces of an object. So that's why if an object has a surface that is rough, like cement, it is harder to travel across it with a sliding motion, because it has lots of really big areas for you to catch on and create bonds with. If you have a surface that has a really smooth feel, so like ice or glass, you have a lower source of friction because there are smaller valleys and peaks to create those bonds with. So what affects friction? The surfaces that are touching changes the amount of friction present. Each surface has a specific coefficient of friction that signifies how smooth or rough a surface is. So with your car, you have rubber tires, because rubber grips the cement really, really well and has a very high level of friction. In addition, the weight of the object you are applying a force to affects friction. Again, back to that dresser example. If you're going to move your dresser across your bedroom, it's a lot easier to do that once you take all of the drawers out and just move the empty dresser and then put the drawers back in. If you want to move the dresser when it's full of clothing, it has a higher weight of gravity pulling it into the ground, so it becomes more difficult to move. So here's how we calculate friction. Objects sitting on a flat surface use the following equation. Ff equals mu Fn. So mu is that coefficient of friction, and mu is this funny backwards y. It's a unitless number that expresses the relative roughness of two surfaces. The coefficient of friction is a decimal between 0 and 1. The bigger the value is, the more rough the surface is. So remember I said unitless. If you solve for mu, you do not have to put newtons or meters or kilograms behind it. You are simply just going to write the number. If it is close to 0, it is a very smooth surface. If it is close to 1, it is a very rough surface. So up in this equation, we are going to do some substitution possibly. So the force of friction is equal to mu times the normal force. But if I draw our little diagram over here, our normal force is the force that's going up, And our normal force so far has always been equal to our gravitational force. And our gravitational force is mass times gravity. So this is just a substitution that we can use in case they give us mass, but not Fn, that we can still use to solve for unknown variables. So Ff equals mu Fn is our basic equation. Our substituted equation is Ff equals mu times m times g. And again, if I give you the mass in newtons, you can just plug that in as Fn, but we're going to look at that in a little bit. So here's a practice problem. A grocery cart is pushed through the store with a constant velocity. The coefficient of friction between the cart and the floor is 0.18. There is 97 newtons of friction acting on the cart. What is the cart's normal force, and what is the mass of the cart? Going back to our basic equation, Ff equals mu Fn. List your knowns and unknowns. Ff is 97, mu is 0.18, Fn is a value that you don't know. So 97 equals 0.18 Fn. Now we have to divide out those two numbers to get Fn by itself. And Fn equals 538.89 newtons. So that's our final answer for this first question. Now the second question, what is the mass of the cart? So Fn, we said on the last slide, is always equal to Fg in problems that have a flat surface. And Fn is then equal to m times g. So I'm going to list our knowns and unknowns. Fn is 538.89, m is our question mark, and g is 9.8. So 538.89 equals m times 9.8. And in order to solve for this m, we have to divide out the 9.8, and m equals 54.9 kilograms. Now, I could ask for all this information in one problem. Instead of having you solve for the cart's normal force, I could have just strictly said what is the mass of the cart. And if I did that, you would have used Ff equals mu mg in one step and still calculated the same final answer. So here's an example problem. A 2.5 kilogram book is being pushed to the right. However, it slows to a stop with an acceleration of negative 0.36 meters per second squared. If the coefficient of friction is 0.2, what is the applied force acting on the book? So step one is free body diagram. We know it's slowing to a stop, so our Ff has to be larger than our F applied. Fg goes down, Fn goes up, and those are the same lengths. I care about the x direction, so I'm going to write F net equals F applied, because remember, our right motions and our upward motions always come first, minus Ff. Now I'm going to make two substitutions. This first part, I'm going to substitute m times a. F applied is going to stay the same, and Ff, I'm going to substitute mu Fn. Now I'm going to make one more substitution, because they didn't give me Fn, but they did give me the mass. So m times a equals F applied minus mu mg. So I'm going to substitute Fn equals mg here. I'm going to rewrite that equation down in step 3. I'm going to list all my knowns and unknowns. And notice I already have m here, so I did not rewrite m at the bottom. 2.5, negative 0.36, question mark, 0.2, and 9.8. Now I'm going to plug all those pieces of information in over here. So 2.5 times negative 0.36 equals F applied minus 0.2 times 2.5 times 9.8. We're going to combine numbers. And 2.5 times negative 0.36 is negative 0.9. F applied, we still don't know. 0.2 times 2.5 times 9.8 is 4.9. And now to solve for F applied, we are going to add 4.9 to both sides. So F applied equals 4 newtons. So even with applying 4 newtons, we are not overcoming the frictional force acting on this book. So we are slowing to a stop, but our force applied is a total of 4 newtons. So from now on, we're going to work with our F net equations, our Newton's second law equations, but instead of just solving or using force due to friction, you may have to substitute in this mu Fn or this mu mg. I'll see you in class tomorrow so we can practice.